We present GRIP, a deep learning model for generating dynamic 3D hand-object interactions based on body and object motion. Virtual humans that move and interact naturally with 3D worlds have many applications in synthetic data creation, games, mixed reality, and telepresence. Motion capture technology is widely used for 3D animation today. However, the data rarely contains hands because they are difficult to capture. Our goal is to transform human motions captured without hands into more natural animations by synthesizing the appropriate hand-object interaction. Previous methods have limitations, such as requiring an initial hand pose that is then improved, considering only single hand grasps, and suffering from generalization to novel object shapes. We address these limitations with our method called GRIP. Going beyond previous approaches, our method first denoises the arm motion and then directly infers dynamic motion of both hands simultaneously, conditioned only on the object and body motion. At test time, GRIP takes as input a sequence of unseen body and object motions captured during an interaction. As output, it generates a sequence of hand poses that are synchronized with the body and object interactions. GRIP's overall task is challenging and multifaceted. The generated motions need to be fully coordinated with the input motions and must simultaneously be plausible, temporally consistent, and lifelike. To achieve this level of realism, we propose two main technical novelties. First, we use a set of virtual hand sensors to extract rich spatiotemporal interaction features between the body and the object. Second, we propose a novel three-stage pipeline consisting of an arm denoising network, ANET, followed by a two-stage hand inference network, which leverage the hand sensors to generate interaction poses. To make this clearer, let's discuss each part in more detail. The hand sensors consist of an ambient sensor and a proximity sensor for each hand. For each ambient sensor, we uniformly sample a set of roughly 1,000 points in a 15-centimeter radius hemisphere that is rigidly attached to each hand and centered at the base middle finger joint. We compute the distance from these points to the closest vertex on the object surface for each motion frame. This captures information about the relative hand-object distance and the object shape. For the proximity sensor, we sample roughly 100 vertices on each hand and compute their closest distance to the object surface. In contrast to the ambient sensor, the proximity sensor provides fine-grained geometric details and more nuanced information about the interaction. This is essential to generate hand poses with fewer penetrations and better contacts. CNET is a novel encoder-decoder neural network. It takes as input the future trajectory information, body motion, and hand sensor features of the current and next frame. As output, it predicts the hand poses of both the current and next frame. For realistic motions, it is important to maintain consistent contact across consecutive interaction frames. Therefore, we propose a novel algorithm named Latent Temporal Consistency to add motion consistency in the latent space of hand motions. For this, the CNET encoder first maps the inputs to two latent codes, a global latent code for hand pose in the current frame and a relative latent code for the next frame with respect to the current frame. We compute the global latent code for the next frame by adding the two latent codes and then decode each individually using a shared decoder to regulate any inconsistency between the two global latent codes and output smooth hand poses. For the hand sensors in CNET to capture rich information between the hand and the object, the arm's motion should be very accurate and free of noise. Therefore, we train ANET to refine arm poses before using them in CNET. As input, ANET takes the arm motion and hand sensor features of the current ground truth frame along with 5 noisy future frames and outputs denoised arm poses. Similar to CNET, we use LTC and ANET to ensure motion consistency in the denoised motions. For this, the encoder maps the input to 5 latent representation for each arm pose, allowing us to apply consistency between them. A shared decoder is then used to output the denoised arm pose for each of the future frames. The motions generated by CNET are reasonable, but can be refined further to improve the realism and remove possible hand-object penetrations. To this end, we train a refinement network called RNet. RNet takes the proximity sensor values and hand motion and outputs refined hand poses. Qualitative results show that RNet is able to remove penetrations and artifacts from CNet results. Overall, grip generalizes well to unseen objects and generates realistic hand motions. Additionally, the results demonstrate that ANet is able to refine the noisy arm poses, leading to more realistic and accurate motions. Furthermore, our method is able to transfer motions from one object to another one. Given a source body and object motion, we replace the source object with a target one, with a roughly similar size and shape, and generate the hand interactions. Results demonstrate that our method generates realistic hand motions for the target object. This can be used to generate synthetic data. In addition, despite training on small objects, we demonstrate that grip also generalizes to larger objects. Specifically, we generate interaction poses for unseen large objects from the InnerCap and MoGaze datasets. Our results show how grip upgrades these datasets to have more realistic hand-object interaction poses. As illustrated here, grip takes easy-to-acquire motion capture of the body and object and adds realistic hands with physically plausible hand-object interaction. This has many applications in animation, games, mixed reality, and synthetic data generation. For quantitative evaluations and more details, please see the paper. Thank you for watching.